Propulsion continues to be normal.
RCP chamber pressure looks good.
Doubling up. Roger, roll, Atlantic.
Water towers can fly!
Tango Delta nominal.
Flight downside, feed off. Bring in, feed off.
Yikes. You bet.
Concur.
We don't need any more of these.
All right, folks, you know the drill. Let me know if you can hear us today. It's time for a special episode of NSF Live. I've got Elysia Segal with me. I'm John Galloway, and we're going to be doing a partnership show here with Intrepid Museum. Wherever you're watching from, we've got it on all sorts of different channels. But let me know if you can hear us and see us over in chat. Give me some 5x5s wherever you're watching. It basically is going everywhere. And, well, we go everywhere too. How you doing, Elysia?
I'm doing great. I am doing great. Quite a week this week, huh?
It's been a little bit of a week. It's been a big orange week, I guess you could say, right?
Oh, yeah.
We're not talking about Halloween.
It was a fiery week, for sure.
It was a very bright and loud week.
It was an explosive week, I think.
A controlled explosion, though. It's a very controlled explosive week.
A controlled explosive week. Yeah.
That ended up with a spacecraft on its way around the moon.
Yeah, it's super close too. I think the closest approach is tomorrow.
It is.
Right?
It
like
is.
80 miles, and then it's going to go even further and then come back.
Following the NASA tracker, I saw they pulled go, no go for the actual lunar insertion or lunar capture, I guess, instead of just flying by and coming back. So that was the thing. Of course, we're talking about the launch of the Artemis 1 mission. You probably saw that here on the channel down at the Cape. A lot to do with that, and I guarantee you we're going to be doing a bit of a recap of that after the mission, I don't know, spend some more time going around the moon. For today, we have a very special NSF Live. You know that we do these NSF Lives in partnership with Intrepid Museum in partnership with NASASpaceflight. Today, we're going to be having some special guests from NASA talk to us. Elysia, you want to tell us a little bit about the special guests?
Yeah, so we have people here today from the Space Technology Mission Directorate. So these are some people that have been actually working on technology that will eventually someday help to inform our trips to the moon and beyond to Mars. Very exciting missions, very exciting work that they have been doing for quite some time now. So yeah, excited to bring them on and hear about some of the very cool demonstrations that they've been doing lately.
Absolutely. We're gonna jump right into it, actually. This is a little bit different. Sometimes we do a pre-show, and the original idea was we let people sort of get into the show, and, you know, it's like filling into the theater and finding your seats. But we're not doing that today. We're going to jump straight in with our special guests at the very start of the show. Housekeeping first. Remember, the NASA Spaceflight / Intrepid Museum Virtual Astronomy Lives don't just happen. They're supported through a NASA cooperative agreement awarded to the New York Space Grant Consortium. So massive thanks to the New York Space Grant Consortium for the support in helping us make these shows happen. Without further ado, let's get our special guests from NASA on the line. I mean, they're already on the line. We're just going to show them to... Anyways, you know how it goes. Friends from NASA. How are you doing? Trudy and Tawnya, it's good to see you.
Hi, guys. Hi. Hi, Elysia.
All right. So with us, everyone, we have Trudy Cordes, the Director of Technology Demonstrations in NASA's Space Technology Mission Directorate. Up there. And then we've also got Tawnya Laughinghouse, Program Manager for Technology Demonstrations in Missions in that division. And their teams, like I kind of said before, they're focused on developing technology and really proving their capabilities for missions to the moon and beyond to Mars someday, because in many ways, the moon is actually going to serve as a proving ground for Mars. So welcome to you both. So excited to have you on the show today and to hear a little bit about some of the cool things that you're working on. You know, NASA is making such incredible technology all the time, but so often a lot of us don't really hear about it until it is actually launching or sending us back, you know, pioneering, groundbreaking information. So you all are really some of the brains behind developing this cool technology. So can you tell us just a bit about what your division does and some of the types of projects that you work on in general? Trudy, we can start with you.
Sure. Just like a good student in school. I always wait to be called on. First of all, before I start, Elysia, I have to ask you, are you wearing parachute and capsule earrings? Okay.
I am indeed. Yes.
I noticed.
I thought this would be appropriate because of the heat shield on the bottoms.
Not only that, but Orion is doing some amazing things right now. I think they're getting ready to do their, lunar flyby, and I think they get like 80 miles from the surface of the moon. And anyway, so I bet any money our audience today is following that closely.
For sure.
Yeah. Well, listen, thanks for having us, me on and us on the show today. I'm really proud of the work we do in technology demonstrations. I would say it's kind of a lesser known program that NASA conducts, and really proud to be a part of it, work with a great team of people. So I'm the Director of Technology Demonstrations. It's within the Space Technology Mission Directorate that's out of NASA headquarters. And we develop and demonstrate transformative, cross-cutting, system-level demonstrations. We conduct them in environment in which that technology needs to operate in the future. And we try to take the technology to the point where it can be utilized or handed off to whatever stakeholder or customer or partner organization will use it. And we have a lot of examples of those we can get into here during the course of the show, including something that we just launched last week, the low Earth orbit flight test of an inflatable decelerator. It's a heat shield, like you stated. And that happened just a few days before the Artemis launch, and it also was a flight test. And so I realized what an honor it was for us to be launched within the same week as another major flight test at the agency. Of course, that was the flight test probably more people were paying attention to with Artemis 1 getting off the ground, but a little bit more attention to. But I do like to think that our technology demonstration got some amount of attention, and it did very well. So we can talk about that through the course of the show. So anyway, again, thank you to be here. Happy to talk about whatever folks want to talk about today on a Sunday, a cold Sunday afternoon. I would think it's safe to say for almost the entire country, everyone's below average temperatures right now where they're at. So yeah, that's it for me.
Okay. And Tawnya, so you work in a subdivision of that whole division then, right?
That's right. Well, specifically, so Trudy is with Space Technology Mission Directorate at NASA headquarters. And I manage the largest program within Space Tech, which is technology demonstrations. So Trudy is program director actually of tech demonstrations, and I am program manager of technology demonstration missions, or TDM for short, because that's a pretty long name. But our responsibilities here in the program office, and we're actually hosted at Marshall Spaceflight Center in Huntsville, Alabama. And so we really work hand in hand with Trudy and her deputy, really supporting all of the advanced technology projects and missions that are within our portfolio. And what we always say is we're looking for them to, have their day in the sun, to advance through their life cycle, properly maturing it so that we can have their day in the sun like LOFTID did on the early morning of November the 10th.
That's great. And, actually, I think we've featured people from your team before, now that I think of it. The Mars helicopter, right? Ingenuity, we had Teddy Zanetis on here. Spectacular episode, actually. He was great. I just saw that flying across the screen in that video that we're showing now. So really, really cool stuff you guys are working on. But yeah, so let's just dive right in now. The big one recently, you've had, like you said, kind of an exciting week and a half now, super successful launch of LOFTID, the low Earth orbit flight test of an inflatable decelerator. Really, really fascinating thing here. Can you just kind of give an overview for people who aren't familiar, in your own words, the people who really worked on it? How would you describe this to everyone? What is LOFTID in a nutshell?
Tawnya, you want to start, or you want me to jump in?
Because it can kind of fit in a nutshell, right? It gets real small.
That's funny.
That is exactly right. So LOFTID is a flight test of an inflatable heat shield, and it's a test of HIAD technology, which is hypersonic inflatable aerodynamic decelerator, which is a mouthful. So we like to say HIAD for short. But all prior tests of this HIAD technology have typically been suborbital, which means it's launched and goes straight up and it comes straight down. LOFTID was actually an orbital test flight, which meant it went full orbit around the Earth, and then it came back, and so the energy was much higher. And one of the things we wanted to know was to see how it performed at orbital velocities. And when you said yes, it's come back. It's made of a flexible woven thermal protection system, so it's very pliable. And one of the things about previous types of heat shields is that they've been like rigid bodies, and a heat shield being launched, previously can really only be as big or as wide as the fairing of the spacecraft that it's being launched in, right? The launch vehicle fairing. What's so special about the LOFTID technology is that because it's made of that flexible woven thermal protection system, it is very pliable, and so it can be folded very tightly. And because of that, you can have more room, more space for other very high mass items that you need for your missions, possibly a crewed mission to Mars. Items like oxygen sensors, like entry vehicles, like rovers, like habitats. You have more space for that. And so that's really what's game changing about LOFTID. Trudy, do you have any other exciting things to say about LOFTID?
Yeah, so this technology was a good decade in the making, and it's been studied for quite a long time. This particular test article is 6 meters in diameter, about 20 feet across. So that's what we tested. It can withstand temperatures about to almost 3,000 degrees Fahrenheit, about 2,900 is the max. I think they expected it to see about 2,600 degrees Fahrenheit on this flight test. And as Tawnya said, it compacts into a smaller space, can fit well inside of a fairing. I believe it can. I believe that the lifetime of the test article from inflation and deflation, because there's a few inflations on the ground they have to do to test it out. So we do extensive testing on the ground with all of our technology demonstration missions. It goes through as many environmental tests as it possibly can. As anything we can simulate on the ground, we are going to test it on the ground to reduce risk that it succeeds during its environmental flight test. And so we did a lot of ground testing, and I think it can inflate and deflate around 6 times total. And so what other particulars I'm trying to think of that you'd be interested in. So this test article, I believe, could bring back. So you have to think of it as an upside down parachute. It protects the thing behind it. And it can bring back, I think, on the order of like 1,000 to 2,000 pounds of mass. We do need to scale this up for future technologies future needs, really on the order of 50,000 pounds for some applications. And to do that, we're talking test articles in the future that would be on the order of like 12 meters in diameter and 18 meters in diameter of scale up for different, again, applications. And this was a great partnership. LOFTID was a great partnership with the company, United Launch Alliance. They are developing and are near ready to launch their next launch vehicle, Vulcan. And they're looking at this to bring back their first stage engines from Vulcan, and to do a midair recovery even, so that they never hit the water or never hit land. They recover them midair and are able to take them back, refurbish them, salvage them, and it's a big cost savings for them. Then it becomes a big cost savings for their customers, and we're one of those customers. so that's how you reduce the cost of access to space, the cost of launches are things like this. And that's a very practical application. And then for NASA, its future missions would be landing large scale masses on Mars, much larger than we're landing now with rovers. So large scale cargo. And potentially humans, even someday in the future. So when you think about Artemis and the progression of that as we go into the future, these are the types of capabilities that, without them, some of our future missions are not possible. The things we're talking about now as an agency, those things that are on paper are not yet feasible technology-wise. So that is the importance of investments in technology demonstrations like this. We do a lot of the, non-recurring engineering. We take care of the costs that a lot of even companies don't have in their research and development kind of budgets to do, and we partner with them. It's very, I think, it's very synergistic and very kind of symbiotic in how we do these things. So what we're doing today with these investments, we help ourselves later, and when we're able to go back and buy these things at a cheaper cost to ourselves, and we gain capabilities we don't currently have.
Yeah, that's so fascinating. I know the idea of just keeping cost down, obviously, and that reusability factor is so important as we proceed towards all of these missions. And that's so fascinating. So you said 6 times you think that they would be rated to be reused. So is the idea then that, let's say with the Vulcan engines coming back, is the idea then that the engines would be, inside this little shield, it'd come in and it would splash down in the water, like the actual shield would splash into the water, or would it be caught in like another raft of some sort, or would it float, I suppose, and then they'd pick up the whole thing in the water with the engine inside?
So I think the idea is to do a mid-air recovery by helicopter so it never touches the water. So right, it grabs it. Yep.
And for the other types of cargo that might be used for as well, the same thing, it would always be a mid-air recovery? Not
necessarily, no. I think in that case then it would have some parachutes that slow it down through that kind of subsonic regime. The high-ed technology can take the velocity from, like, say, a Mach 29 to about a Mach 0.7. So you still have to slow it down after that with parachutes and then land it where you're going to land it. But no, I don't expect that we'll have mid-air recovery for all of our applications.
And then once that happens, though, and it is recovered, then theoretically you could reuse it a few more times, maybe, if it's rated for 6 inflations.
I believe so. So. If you find you have to inspect it, of course, that's what we're doing now with LOFTID. The test article is on its way back to Virginia, to Langley Research Center, where it was developed, and they'll inspect it. And one of the things with this particular flight test was they have to look at what damage was caused just by reentry, by temperatures, or the velocity reduction that had to go through, the forces it sees, versus what was caused by any splashdown in the water. They have to discern that from this flight test.
Or also the helicopter recovery too. I'd imagine if you're swinging a hook around, you don't want to puncture something inflatable, right?
In the future, once that's done, you'd have to look at all of the aspects of operations to see where might the damage have occurred before you can determine, like you said, if you can recertify it for future use.
Yeah. A real quick question, just to clarify for some people watching. We're not just looking at CGI presentations about what we're going to do with LOFTID. I mean, LOFTID has already launched and has already come back, right? There's a video about this.
Absolutely.
Like, this actually shows LOFTID being recovered after it went around the Earth one time and then re-entered the atmosphere and splashed down at sea, correct?
Correct. That's not a cartoon. That is not artist rendition. That is actual. Yeah.
That's what actually happened a week and a half ago.
Yeah. I love this because it's got like a hand on it, like somebody is grabbing a hold of it, like while they're wearing a helmet camera or something.
And this is it, that was it coming down with a parachute as well, I believe. Is that right?
Yes, that's the infrared imagery as you see it approaching the ocean.
There it comes. So something that I'm really kind of curious about then is this actual, you said the flexible thermal protection system. So this fabric, I suppose, this outer layer that has the ability to withstand all of this temperature, crazy amount of friction that's coming in through the atmosphere. What's that actually made out of?
This woven protection system. Trudy, I can't remember the actual name of it.
It's a Xylon. It's a Xylon material that makes up the netting and the kind of web material you see on it. Very strong. When it's inflated, it's extremely rigid. It really almost acts like you would a rigid metal structure. That's how the strength of it.
Absolutely. I think, Trudy, when if you were to knock on it, this is what to me is so amazing about this material. If we were to just knock on it, it would sound as if you're knocking against steel. I mean, it's amazing, when it is put together. So, it is not like a bouncy castle.
We're not going to rent it out for birthday parties or anything, right?
Right.
That might hurt. It sounds like, geez, if you jump on something like that, that's hard. Geez. But that's really interesting, though, that a material, I mean, this is the stuff NASA does, right? You come up with these fabrics that do incredible things like that. Do you think this is a material that then might be looked at to, I don't know, somehow coat actual, spaceships too? If it's not just, something like LOFTID coming in, this inflatable thing. I mean, I work with a space shuttle,
right.
So they had, the thermal protection tiles and everything underneath it that, it comes in belly flopping basically. So do you think that this material is something that could be looked at to use on actual structures as well that are coming in too?
Absolutely. And this type of research has been going on for quite some time, Elysia. And even though, in TDM, where one of the things that we love to say is that, technology drives exploration. We're advancing those technologies that are going to help us with our exploration goals, our future mission plans, really enabling the nation and the agency. But, another huge objective for NASA is that we directly align for space tech programs like TDM. We directly align with NASA's strategic goal, to develop technologies that will improve the quality of life on Earth, be for the benefit of all mankind. And, a prime example of this is a potential spin-off technology from the flexible heat shield material that was developed for LOFTID. And so NASA previously with USDA, the United States Department of Agriculture, actually developed a prototype to improve fire shelters to help protect firefighters using the exact same materials that are used in LOFTID. And that's just one example of what the benefits of this material, but so many different applications, that can be used, but that's just one of them.
Yeah. Oh, wow. That's fascinating. That is really cool. All these things that NASA comes up with that we do use here on Earth. That is the best argument when people say, why are we spending all this money launching stuff into space? We use it here on Earth too. That's the answer, guys. That's what it is. So LOFTID was really created in partnership with a number of other divisions as well, right? I mean, you had, people working on the instrumentation on board. You had the fiber optic sensing systems, the temperature sensors and everything. What's it like working so cross division, being able to do that with all of your other colleagues in other divisions as well?
Well, that's I think one of the goals of space tech is that, we're certainly looking for true public-private partnerships to, enable these technologies and move us forward. And LOFTID is just a prime example of that, public-private partnership with NASA and with United Launch Alliance or ULA. And, the primary project team for LOFTID is out of NASA Langley in Virginia, and we've had significant contributions from other field centers like NASA Armstrong, like NASA Ames, right here at NASA Marshall Spaceflight Center, who led the avionics for LOFTID. Just a true public-private partnership. And then, of course, we had other, U.S. vendors who supported this Jackson Bond out of I believe it's New Hampshire. Correct me if I'm wrong, Trudy, who supported the flexible heat shield material, helped build the aeroshell for us. So just a true public-private partnership. And so, one of the goals is to help support U.S. industry to enable them to help make that access to space easier for all.
Yeah. So let's see. Are there any questions, Das? Oh, yeah.
I was actually getting ready to put on my camera and raise my hand because there's a lot of questions that people have been coming through with. Folks, remember, if you have a question, you can tag us in chat, or you can just put the word question in. If you're watching on YouTube, make sure you tag at NASASpaceflight to get your question into our question software. But we do have quite a few, and I think the biggest one that I'm seeing here is that we might have some Moose fans in the chat, either that or Kerbal Space Program players. So some people were asking, quite a few people actually, asked if a person was on the other side of the LOFTID heat shield, could they have rode it down? And this, of course, goes back to an old concept, man out of space easiest, in the early days of NASA getting people out of space, where they were like, how could we get an astronaut down just the astronaut part, with actually an inflatable heat shield that barely fit a person. So I don't think that was a design goal of LOFTID, right? But
similar, though.
how did the temperatures, or how did the environment behind the heat shield compared to the environment in front of the heat shield? Maybe if we frame it that way.
So I do think that we have some analysis to do on all of the data that is going to come in from LOFTID.
Right.
The only, preliminarily, all I'll say is, and I said this, I think, last week talking to some media, which is, the goal of any of these technology demonstrations is to see, does it work?
Right.
And the answer we got so far was yes, it inflated. It was oriented properly. It came down through the atmosphere. It didn't break up upon seeing the high temperatures or melt or anything, like that. It withstood all of that. So preliminarily, the concept, works.
Right.
But there's a lot of data reduction and data analysis that we need to do. And that is going to take the course of the next many months to do, and look at the sensors and look at the various instrumentation that we have on the heat shield to see what it was, what the results were of that.
What it was like.
I'll say though too, when the question of could someone have ridden it down like a roller coaster? So, like on the back of it. Right. I mean, it depends on what exactly you're talking about by riding it down. I mean, you would need your own life support systems behind that. You couldn't just grab on and be like
hold on to
yourself in like it's a roller coaster or anything. Be like, no, that would not be good for you. But certainly we are looking at it to land humans eventually on planetary surfaces that do have atmospheres. So that is the thing about LOFTID, is it needs an atmosphere because you have to create drag on the vehicle to slow it down.
Right.
So on those planets, the moon, you don't need a LOFTID. You're not going to use a LOFTID.
I've done that in Kerbal. Like, I've tried to go to the moon and use my parachutes to land on the moon, and you work out really quickly that doesn't work very well. Lacking an atmosphere.
Is this a video game you're all talking
about?
Yeah,
Kerbal Space Program is a video game.
Sorry.
I was feeling a little left out too, Trudy. I was
like, moose? I mean, you said something like moose and Kerbal. I'm like, I don't know. My kids, hold on. Let me go get my teenagers and see if they can explain.
We are going to have to play some Kerbal together, I think. Kerbal Space
Okay.
Program is a video game that's based on real physics, and it actually has a part in the game that is an inflatable heat shield concept that looks almost exactly like LOFTID. And you get
What?
the exact same things from it. It folds up really small, and then you get into space, and when you're coming back down, it expands, so it has a lot more drag, and it's better than a, there's also, that is a part in the video game that is about real physics. So I didn't mean to catch y'all out. The audience
I feel like
knows.
that's going to put us out of business. I feel like that's like a NASA going out of business. No, I'm just kidding.
We're trying to supply you with more engineers in the future.
Yeah,
is what we're trying to do.
it's the engineers of the future. It's the people that are going to be taking your jobs eventually, really.
I do like that.
There
I
you
would
go.
like a succession plan so that I can retire sooner than later. I will say this too, and at some point we could talk about that, but it's kind of going totally off on a different topic. I do have a concern. Are we graduating enough engineers in this country? Are we graduating enough in the STEM, area? Do kids shy away from these things for whatever reason? I see it even with my own kids who are very good at math and science and still shy away from, some of these types of things. And so that is a concern of mine. If video games will get people interested in it and applying to, curriculums, where I'm all for it. So keep on doing your video games that are really cool. They sound cool.
Yeah, it is. It's really cool because it's based on real physics. So it's not like, swipe to get to orbit or anything like that. Those sorts of games. It's very much like a calculate the delta V given this amount of fuel and this amount of non-fuel dry mass and this type of engine with this ISP. Like the game calculates all that. So it really does inspire.
That is educational right there. That is educational. I like it.
I'm about to load up Kerbal. We'll just play Kerbal for the rest of the show here. We'll build LOFTID in Kerbal.
Okay, that sounds good.
I do have more questions here, though. We could talk about that for an hour. As a disclaimer, I've played that video game for somewhere over 8,000 hours. I used to do it for a living. Like I played Kerbal Space Program online for a living, teaching people the basics of physics and rockets and stuff like that. So it is a real thing. It's not swipe to go to space. So there was a question about the type of LOFTID technology and how this sort of works out. Is this a NASA thing where NASA owns this inflatable heat shield design now, or was it NASA funding a private company that then designed that, like happens sometimes? Where does that sort of fall on the chain of whose tech is that?
Trudy, go ahead.
Okay. Yeah, no, NASA, this was the brainchild of some NASA engineers. NASA Langley does own the IP rights, intellectual property for that.
Right.
We work with companies who are trying to use the same technology and license it, from us. And so we work out, our lawyers get involved and work out data rights and things like that. And that's how we, without disclosing too much about LOFTID, we're in the middle of some things on that, but that's how we do those things. But it just depends. I mean, sometimes the ideas come from NASA, not all the time. And I'll tell you, NASA has really embraced this thought that good ideas can come from anywhere. I've never seen the crowdsourcing that we do. We do these challenges, prizes and challenges. We have a whole program around public prizes and challenges that we do when NASA's like, hey, we need this problem solved. You guys help us. And we put these out. You guys should go look at our website on these things. And we put them out quite frequently.
Yeah.
And I would tell you earlier in my career when I started, I've been with the agency for a long time. We didn't used to do that. We didn't embrace that philosophy, and it's very much a part of the culture and what we do now. So I don't know if Tawnya wants to add any more to that, but.
No. I think you hit that, Trudy, and I think and if I could go back to one of the points, if you don't mind, Das, just sort of shifting back to where we were before and talking about LOFTID and actually landing, on the surface. What I love and what I just think is so amazing about it is, naturally when a spacecraft is approaching the surface of a planet, it starts going extremely fast. I mean, it is coming in hot.
Yep.
And that's because the planet's gravity is pulling it in. But of course, we want the spacecraft to land safely, right?
Yep.
So we have to completely slow it down. And as Trudy said before, the heat shield really helps overcome that drag and helps slow it down before it touches. And it counteracts the pull of gravity specifically. And so it slows down the spacecraft. But heat shields can actually slow an entry vehicle going 10,000 miles per hour to about 1,000 miles per hour in 60 seconds.
Wow.
It's just amazing.
It's like seriously slamming on the brakes by, I guess, slamming into the atmosphere, right?
Exactly. I just wanted to get that in because I just think that's such a cool aspect of heat shields.
And it's such a big thing, and we try to use that lots of different places, like even on the way out to Mars, because when you get there, you need to slow down, right? We don't want to poke our way over to Mars at 10 miles per hour. It would take us forever to get there. So we want to be going really fast as we approach it, and the closer we get, the more the planet sort of pulls on us, right? But we have to slow down and actually stop on the surface of Mars. Nobody wants a rover that turns into rover vapor when it hits at 100,000 miles per hour or something like that, right?
Exactly.
So you've got to slow down, and in order to do that, you have to expend energy somehow. You can carry fuel along, and then you can point your engine backwards and burn your fuel and slow down that way. You've seen parachutes happen before, but the parachutes might get ripped off if you're going too fast and you deploy them too soon. We've talked about heat shields, but when we go into the atmosphere of the planet like that, it really gives us the ability to sort of get free deceleration. I say free, right? But using the atmosphere instead of trying to use fuel or something like that means that we can slow our spacecraft down to where we can use the chutes or something. And heat shields are why we can do that, right?
Absolutely. I've got this little model here of our little lofted heat shield. And what I know you were showing pictures of it retrieved on the boat, right?
Yep.
But I was listening to the engineers and part of the team talking about LOFTID and how it looked so pristine, right, Trudy? I mean, they were saying that it almost looks like it could be reused again, coming in and surviving those entry. I think they certainly saw a little bit of charring and probably with the this nose part coming in first through the atmosphere. But I'm excited to hear it's probably going to take a good year for the full analysis to take place for LOFTID, but we were all just so pleased at how it performed.
Yeah, they are saying it. They did use that word pristine. They are saying it looks pretty good. And back to Tanya's point about landing, which is cool. I didn't even know the fact that you mentioned. But the other thing with this type of technology, because it slows down faster, you can use it to land at higher elevations. And one thing we learned with Mars 2020, which is the Perseverance rover that's on Mars now, that also technology demonstrations had quite a bit of we had some technologies on that too, and I can talk about that in a minute if you'd like. But we've learned it's very important for our colleagues in the science mission directorate, the scientists who are looking at these things, and the principal investigators who aren't necessarily even, part of NASA. We get our principal investigators from academia and other places. It's very important for them to try to land as close to the scientific area that they think is worth studying for many reasons. And to traverse a planetary surface is much more difficult. It's very difficult. And so the closer you can land, it benefits them. So I think the HIA technology opens up some of that too, just like a technology that we just tested out on Mars 2020 called terrain relative navigation, which is a system of sensors and algorithms that we used for the very first time on Mars 2020 to pinpoint a landing spot that the scientists wanted us to see us land at. And it does triangulation and it has onboard maps, and it knows where certain hazards are. So it's hazard avoidance, but it's also optimizing where you're going to land. And it pinpointed that landing spot, I was told, within 6 seconds.
Wow.
And sure enough, that's where it landed. And it was another huge success. It was the very first time we've used that as well. That is not typically standard for us. Usually we do use a system and a technology on a demonstration type mission where it's not primary to the mission. If it fails, it fails. And it's like a do no harm, type of thing to the primary mission. But TRN certainly was used for that mission and quite successfully. So that was another thing. And just talking about the LOFTID, the high-end technology and where it can help you land reminded me of TRN. I wanted to just mention that too. So
really quickly, y'all might be able to help us decide something here. We always sort of argue back and forth with the viewers if something has landed or not, right? And LOFTID just splashed down in the water. But is it still officially a landing when you splash down in the water, or is it like a watering? We'd let NASA leave that definition up here. Like y'all's decision. Tell us what the right terminology to use is.
A watering.
I've never heard the watering.
You've never heard of watering. Okay. So it is still officially, per NASA, a landing if you land in the water. Water in the water? I don't know.
Tawnya, I've never heard watering for a landing. Have you? It's just landing.
I've never heard of that.
Okay.
Never heard
Water
of it.
landing.
It's a water landing. It's a water.
Okay, water landing. Water landing. Also, too, I have to question possibly. I think you have a great audience. I can't see them. I don't know who's out there.
They're here.
But I'm not sure what kind of time people have on their hands if they're worried about watering versus land. I'm just kidding. I'm
going to tell them that. Next time somebody argues about that, I'm like, y'all have way too much time on your hands, folks.
I would not worry about that, and I'd go play the video game. That's what I would use my time
There
for.
you go.
Excellent.
There you go.
Go play the video game.
I also want to bring... Go ahead, Elysia.
No, I wasn't saying. Go ahead.
I also want to bring... Oh, wait. Yeah, we're good? We're good.
I did have one thing I wanted to say, Das, with my previous career before coming into TDM I was a materials engineer and working pretty much high temperature materials, and so I supported the solid rocket boosters for shuttle, and then supported SLS until I left about 5 years ago. So 2 minutes into launch, our boosters are peeling off and landing into the water. So I'll fight anyone who says that a water landing isn't a true landing.
There you go. Did you hear that? Tawnya says that it is a landing.
There you go.
I appreciate that. A landing.
And I'm just gonna say, Tawnya is the most gentle, kind person I've ever met. So if she says I'll fight you, I mean that's serious business. That is serious, because she is. There's not any kind of violent bone in her body. So that's funny stuff. And you know what? Well, Tawnya, it's funny too, because it seems like eons ago, but I used to work Orion as well, the capsule that's up there now that's getting ready to orbit the moon. And I was responsible for working with our corporate partner, Lockheed Martin, the prime on Orion, on the test and verification plan for that. Again, it was many moons ago, but a lot of us at NASA, we move around to a degree. Sometimes we're working human exploration, sometimes we're work science missions and space technology, and so you find that sometimes you move around in your career and it benefits you. Working on the test and verification plan for something helped me come over here and work on technology demonstrations, which is by and large a test program. But if you're monitoring what's going on with Orion now and something doesn't work, don't mention it to me. I had nothing to do with it. All right, we can
really
get back
cool
to
that you guys got to jump around though. This really must have been quite a week for you. Just all of your projects, doing all of the things. That's really
I used to work closely with the engineer who came up with the encapsulated service module concept with the fairings on the outside that's separated. And when the fairings separated, I sent him a congratulatory email. I haven't worked with him in, it seems like, eons. but you still remember those days and you remember those people. And I remember the brilliant ones I've worked with. There's so many of them, but it's just hard to forget some of the people who come up with these concepts, and I have the most admiration and respect for those folks. So yeah, just staying up till the middle of the night, and I didn't stay up all night. I waited for pharynx separation, and then I don't know, went back to sleep or something. But yeah, we get to do a lot of cool things, Elysia, in our jobs. I'll say that.
It's a great time to be working for NASA. That's for sure. Great time.
So actually talking about that then, with the way that it was sent up with the pharynx separations and everything, with it being packaged then with JPSS2, was that intentional then? Is this was it planned long in advance? Oh, these two are going to go together? Or was it oh, there was some extra room and this thing's a little squishy right now, it'll fit nicely? How was that decided to kind of partner with that for that mission?
I'll start, and then Tawnya can jump in. And it's been planned for a long time. It was planned about 4 years ago, and they had extra mass. They could take us along, and it worked out with being attached to the Centaur. And so a lot of times what happens in technology demonstrations is we try to keep them on the lower cost side, which means we're looking for rides to space. And we look around for what's out there. NASA has something called a flight planning board that meets regularly. And we brought it up to a flight planning board meetings, and we asked what's out there. What is flying in this approximate time frame? What might work? We need, this mass, and they said that works for us. So really it came about through conversation and discussion and collaboration and talking about these things, and it materialized that way. So yes, it's planned long in advance. And the particulars of it worked out, and those are some difficult particulars when you have interfaces for power and structure and electrical, thermal, all kinds of requirements for your payload. Those aren't necessarily easy things to find because sometimes they're pretty unique. But yeah, it worked out great for us, that JPSS2 partnership, and with NOAA.
Absolutely. Nothing to add to that.
I think that what's really also really pioneering about this whole, and not pioneering because you said it's been around for a while, I guess, this idea of the inflatable, the high-end technology, though, that was really something, the first time for me anyway, really, that I'd seen something demonstrated in such just a really fascinating, graceful sort of way was with JWST, right? You had those huge solar arrays that were packaged up real tight like origami, and then spread out later. So something that is inflatable or expandable later on, it really does help being able to package everything nice and tight to save space, because space is definitely something that they don't have the luxury of. I say space, that's funny because it's going into space, but the extra space in your thing to go into space, that's really, really important. So LOFTID is I hope the first of many of these. It was really cool, that video I think we have too of it, expanding to, it's stunning just how large it is. It's what, 20 meters, is it? Or 20
feet, 6 meters.
20 feet.
20, yes.
Yeah, 20 feet across. And when it's all kind of collapsed inside itself and real tiny, is that it's much smaller. It's how big is that?
I want to say what's in my head right now, don't hold me to it, but I think it's 4 by 4 by 7 feet. Is that about
That's right. That's right. Yeah, that's what I'm recalling too, is 4 feet across, from 20 to 4.
Wow.
Yeah.
That's a big deal. That's amazing. So tell us about some of the other things that you all are working on then. LOFTID, 100%, great job. We're so excited to see all of the information as it comes in, to see the future applications of this as well. What are some of the other things you're working on now for the future?
So Trudy, well, one of the missions that we actually have a few that are coming up, I would say. in 2023. One of them that we're really excited about is our Deep Space Optical Communications, or DSOC for short. And that's led by one of our teams out at NASA JPL, Jet Propulsion Laboratory. And it will, continue to help revolutionize the data rates that we get further out into space. And it's kind of like, it's almost like in many ways, it's in our, we have technology thrust areas, and optical communications is one of those thrust areas. And as a matter of fact, just if I could jump back a little bit, but back in December of 2021, we launched laser communications relay demonstration, and that was TDM's first optical communications demonstration, which of course was to sort of supplement the radio frequency way that we send data back to Earth. This is a kind of a new and improved optical communications using lasers that could help take data from various spacecrafts and, send it into the LCRD spacecraft, and then down to Earth in one of our two ground stations that we used for the LCRD demonstration. And so DSOC is kind of a another aspect of that optical communications, moving that technology even further. And we are launching with another host spacecraft. It's the Psyche mission, which is managed out of NASA's Science Mission Directorate. And we talk about partners. We have external partners, but we also have internal partners. And that's a huge mission with NASA Science Mission Directorate, Arizona State University, which provides the PI for Psyche, and it's the heading out to an asteroid called Psyche, which I love to talk about scale. And this asteroid is about the size of Massachusetts, and so it'll be going out to that asteroid to see if there's a metal core in the Psyche asteroid. And so there's all types of instrumentation on the spacecraft to take samples and verify that. But DSOC will be catching a ride on the Psyche mission, and so we're extremely excited about that.
Yeah, I think many of us have been following what's going on with Psyche and all of that coming up. It is really, really cool.
It is. Trudy, I didn't know if you had anything else you want to add about.
Yeah. So Tanya's right. Optical comm is big for us. I mean, imagine that, the communication, the technology used by, Neil Armstrong to say that's one small step for man. That's one. It's the same. That's the baseline technology we're still using today, is radio frequency communication. And to bring in another type of communication technology and be able to do bidirectional and increase our data rates, and be able to just have a more efficient way of communicating is going to be really important for us for the future. So the one up there now that's operating for about the next 2 years, running various experiments back to ground. A couple of ground stations we have, one in California, one in Hawaii, that they're communicating with, and then back up. Then we're going to put a terminal on the International Space Station called Illuma-T, and then we'll be able to communicate from our LCRD payload that's in geosynchronous orbit to the space station, to this terminal, and to the ground and back. So
that's the relay.
That's the relay, yeah. So that's what we're doing. So that's all very important. I'll just mention a couple of important areas for us. Satellite servicing is another big area for us in space, servicing, assembly, and manufacturing. So being able to make, for example, the next great telescope that we do, making it in space instead of making it on the ground, going through all the testing you do on the ground and then launching it, launch all the materials you need and make it up there. So that's one concept. The servicing part of that is if you have an asset on orbit that gets into any kind of trouble, you could go and fix it, or you could refuel it, or you could augment it, or relocate it, a number of things you could do. So like a toolkit in space. we're working on that technology as well. Industry is very interested in that. Other government agencies are very interested in that. Huge effort for us right now. We have 2 major projects in that, launching in the 25-26 timeframe for those capabilities. And then the other one I'll mention is cryogenic fluid management. It's another big area for us. And so being able to reduce boil off for the fuels that we use on orbit is another big area for us. So storage, transfer, and mass gauging are kind of, sub-elements of that overall umbrella kind of capability area that we're working on. And then nuclear power and propulsion is huge for us right now, and all the formulation work we have going on in that right now. That'll be big, how to survive on the lunar surface with power needs that you have. A fission surface power system is going to be, important for that. And the nuclear thermal or nuclear electric propulsion are things we're talking about now and looking at. So a lot of different huge capabilities areas for us that are in our portfolio that Tawnya and I get to work on, and there's a lot to do.
I'm looking at questions in chat here, and I want to roll something up for everybody that is watching right now, right? We're talking about DSOC and these communications, new communications technologies, and it's literally things that you may have heard about in science fiction that this team is working on and making fact. Like you watch The Expanse, right? And they're like, oh, let's open up a tight beam to whoever, right? And they're talking about this point-to-point communication. It's a laser in The Expanse. That is literally what DSOC is. It is using lasers to communicate on a tight beam. You could call it a tight beam if you wanted to, from one point to the other, where you take all the energy in your transmitter and you focus it into a laser beam and you send it to one point instead of RF, like radio waves. When we communicate with our spacecraft using radio waves, we sort of like just send radio out in this big wide pattern, and the spacecraft sort of gets it, and it's like and it sort of sends it back. I mean, we try to tune it and we have like narrower beams there, but if you can do that with lasers and you're able to establish the link and send all your comms on a laser beam, you've heard about it in science fiction. That's literally what y'all are working on. I got that right? I didn't make that up.
No, that's how Tawnya and I talk about it. If we weren't in front of an audience right now, that's what we would say to each other. It'd be like, Tawnya, that communication we have, that's, we're trying to make that better.
We got to fix that.
Exactly, on a daily basis, how Tawnya and
How
I
did you know,
guys?
How did you know?
We need to open a tight beam to Palomar. Yeah, we need to open that. Let's get that broadband tight beam to Palomar and download the data like I could see y'all on the movie screen, right?
Yes, I love it.
But
I love it.
The point I want to make is y'all are literally working on technologies that currently only release or maybe only exist in science fiction, or we've heard about them because of science fiction, and we've read books and we've watched movies, and you work with making those things real or even more available or testing them or whatever, right?
Right. And you just reminded me, when I started off as a high school student, I was fortunate enough to be in a program for high school students here at Marshall Spaceflight Center.
Nice.
Called NASA SHARP, Summer High School Apprenticeship Research Program, and a huge program. And it's been kind of full circle for me because, part of that program, you come in, you get assigned to an engineer or a scientist, and you do a project for about 6 weeks and then present it. I mean, it's really cool for a high school student, as you can imagine. And my very first project working in that was optical data collection techniques and analysis. I mean, that was my project. And, I got to work with, lasers and, setting up the whole system on a hydraulic table and all of that. And, to be, last December, almost a year ago, to be launching, laser communications relay demonstration, our optical comm, was just, I can't even describe, how that felt. It was truly amazing. And so, this, and I won't say that my little project was the precursor for LCRD, but it's in the class. It's in the class of that. And so, just instilling that those techniques and that research and just carrying it through the career, it means a lot. And and of course it shows just NASA's commitment to trying to inspire and, really bring in the next generation of scientists and engineers that they continue to this day.
Yeah, it really is. I mean, we have a lot of technologies on the ground, right? Things that get developed and tested, and, you can make laser communications on a hydraulic table in the lab or whatever, but at some point, somebody needs to do it in space. Because it's cooler when it's in space. And that's literally what you're doing, taking that concept and putting it in space, right? And then how can we use that in space, whether it's the LOFTID inflatable technologies. Who hasn't inflated like a pool raft or something? Well, this is like a pool raft in space, right?
What it looks like, too, when it inflates. It actually really does look like that.
Yeah.
Right.
Yeah,
because...
Go ahead.
Yeah, I hope... Well, no, I hope three things. When we test things on the ground, and I said, we simulate as much as possible. Microgravity is the thing we cannot simulate here. We can do temperatures, we can do pressures with thermal vacuum chambers. We can even put astronauts in a pool to try to give them the kind of motion that they'll go through. But microgravity is one that you cannot simulate here on Earth. And the other thing is, back to what you said earlier about, we're doing things that, you guys see in science fiction. I'll just say it depends on which science fiction. This is why I do not watch space movies. My husband knows I cannot watch space movies because I sit there and I go, that's not possible. What are they talking about? What is Sandra Bullock doing right now in this spacesuit, and like she's floating? And so we're still bound by the laws of physics, right? So I just want to say that, like, yes, in our program, but like if you think we're going to beam someone up soon, not in my program. It's not happening. So, I swear,
Oops. We might have a very brief hiccup.
Every session I do, I get this question.
If I had to guess.
I don't watch them.
Oh, we got you back.
I don't.
Okay, Trudy, we lost you for a second, but you were talking about realistic...
Oh, that I don't watch space movies.
Yes.
And so I get the question all the time of what's my favorite, and I say I don't have one because I don't watch them. I swear them off. Anyway, sorry.
It would still make a fantastic show, like if we were to watch them and then say, what is this? Seriously? That's not how that works. That's not how any of this works. That would be good content.
You know that show where the little guys were in the corner and they would critique the movie?
Yes,
Mystery Science Theater.
Yes, Mystery Science Theater. That's a great show. That's you guys.
We need that for space movies, and we can sit there and critique and be like, that's not possible. What are they doing?
Oh my God, I'd watch that.
All right.
I'll take all of our Zoom cameras and put it down at the bottom, and then I'll just make it like a black silhouette, and then we'll put a movie on in the background, and we'll just yell at the movie. Y'all down?
All those
take us way off track. I'm sorry. You can get back to normal programming.
It is okay. It is absolutely okay. I think a lot of us feel that way when we're watching a show or something. We're like, they did what? What? They redirected the power flux to the cyber cortex? Like, seriously? That's not a thing. Like, I think we would get along watching movies with y'all.
Too funny.
Oh, geez.
Do you have any more questions, Des?
I do. I have an awful lot of very technical questions about LOFTID, and I don't know if we can even answer all these because they're still reviewing data and stuff like that. But let me hit a couple of these really quickly. This one might be a little bit more technical, but we know that when a spacecraft re-enters the atmosphere, sometimes it goes through like a comms blackout because the environment around the spacecraft, the plasma blocks our signals, right? And sometimes, like when the space shuttle was coming back, we would have periods where we wouldn't be able to talk to them. And then TDRS comes in and you can look up your tail cone and stuff like that, and technology marches forwards, right? But does having a larger surface, I guess, on the forward side of your re-entry make it easier to communicate with the spacecraft somehow? Maybe via an antenna looking out the back of the heat shield. Was there anything like that? Like, did you have comms blackout with LOFTID when it was re-entering?
Trudy, I don't think that they, I think that's a part of what we will have to be, looking at. But, there were redundant, communication, instrumentation on LOFTID, the ejectable data recorder, which I think was so neat. It's like the size of a large lemon.
Yep.
That shot out and landed, and you had the ability. The team, of course, had to go retrieve that, and I think it wasn't found too far from the air shell, Trudy, right, when it landed, and we all laughed about it possibly getting swallowed by a whale before it was. There it is.
There it is.
That's the injectable. Yeah, that's the injectable. So they'll be reconstructing data and looking at all of that. More to come. More to come on that.
Yeah. And they had real-time telemetry that I know they were able to get back during the demonstration. The comm you're talking about, I think, would be something. First of all, I can't answer it right now.
Sure.
We would have to, I think, understand more about the physics of all of that. And I'm sure that we have really smart people who are already thinking about what a 12 or 18 meter diameter heat shield and the comms blackout or not that you would see during that reentry phase. But I don't have the answer to your question right now.
Yeah. But
like Tawnya said, TBD on that one.
It's absolutely fine, because the coolest thing for me is we're talking about something that you've done, right? We're talking about LOFTID. The spacecraft's gone up, it's come back down, the heat shield worked, and you recovered it. And now all these people in chat are saying, oh, does it help with this? Does it help with this? Like, there's all these ideas that spring from this one test, and that is exactly how science and engineering works. You've proved that this works, and now all these other follow-up ideas. I guess we're going to need more LOFTIDs or even larger heat shields, right?
Right.
We're going to need a bigger LOFTID.
We're going to need a bigger LOFTID. And then the shark's going to bite on it. Wait, that's a different movie we'll comment on. No, but that really is awesome that you've demonstrated this one technology. And I want people to understand, it's not like, okay, now we're going to buy LOFTIDs and start slapping LOFTIDs on all these things, right? It's not specifically about exactly LOFTID. It is, does an inflatable heat shield work the way we think it does when we get... It's not ground truth, and then it landed in the water, so it's still not ground truth. We get real-world experimental data.
Right, Doss. We wanted to know, could it slow down and survive reentry?
Yep.
I mean, that was question number one. And, from what we were able to see and recover and what we're looking at, those you've got the pictures.
Yep.
It was able to survive reentry. And so, that's where we now, because this is a scalable technology, this is where we'll take what we learned and hopefully, scale it up. And I've heard the, ULA executives say, in terms of perhaps, asset recovery, like a Centaur, a Vulcan engine.
Yep. Smart reuse. They've talked about that a lot.
Smart reuse, absolutely. That, like, they would probably want to start around the 12 meter, and again, what we tested with LOFTID is a 6 meter, and so they'll of course take the data and do with it what they need to, and NASA will take this data and do what we'll need to, and I'm sure there'll be all types of applications and things coming out of this.
Yep. I keep trying to bring this picture up. I have to talk about this one more time, because look at the backside here, right? Like, look here at how pristine, if I can actually draw on the screen, there we go. It doesn't look like it's been to space. It's so clean. It was protected, but normally there's charring on the side of it, and there's flame scorch marks, and it really looks like it's done battle with the atmosphere, right? But this right here that did a lap around the Earth and came back down looks brand new.
Yeah.
Also, real quick, are these actually pool noodles down here? They look like pool noodles to me.
What?
They look like pool noodles. Like they went down to the big box store and bought a couple pool noodles, and they're suspending the LOFTID space. I'm okay with it. Like, I'm all here for using pool noodles down there.
That's highly technical ground support equipment.
There you go. Highly technical
ground support equipment that was designed by NASA engineers, and
you can tell it's NASA Blue even.
And it probably is pool noodles, is what I'm trying to tell you, because I don't think there's anything that's not, we're not above using pool noodles for, cushioning the test articles that we bring back.
Right tool for the job, right?
That actually does make me wonder something, though. So right now you're testing it in water, right? You're splashing down. That is a nice kind of softer landing place. If this technology is used on Mars, then is the idea that it'll shield it and then, I don't know, come off and just go somewhere else? Or will it deflate and get sucked up into something, or like will it land on Mars and will it bounce? Like what will it actually do after it slows everything down?
I hope it doesn't bounce. It's not supposed to bounce.
It's not supposed to bounce.
It's not supposed to bounce.
We talked about it not being a bouncy castle earlier, right?
Well,
yeah.
The material,
No,
yes, but
it should just land its cargo. I mean, it should just land it. We would have to again give it help coming through the more subsonic regime. But Tawnya, I don't know if you want to jump in here, but no, it's supposed to land its cargo. Yeah.
Safely.
Safely. There you go.
Safely, which means no bouncing.
It's cool because that sort of thing is for the next engineer to design. Like we know that the inflatable technology works and we know that it can withstand re-entry and we've proven all those things. And now you can take that and say, all right, say we use it on Mars. How do we get the rover off the top of it or whatever it is, like whatever the next thing is? Because step one is proving that it's like maybe step two is proving that it works. Step one is coming up with the idea. Getting funding is somewhere in there. But you sort of understand that now the concept is sound, right?
Right.
Open up all sorts of other opportunities.
Yep. That's exactly the point of a technology demonstration. And Tawnya and I've seen other demonstrations we've done where we realized that we need a next version of it because the technology didn't exactly perform how we expected and there were issues and we need to do some redesign.
Yep.
It's not uncommon for us to say we need redesign or we need to tweak this component. We have some sensitive components. We just flew a couple of years ago a deep space atomic clock, which is like GPS for space, and has really sensitive components in it that were hard to even test on the ground, and found that it worked actually quite well, performed quite well. But they know now from that there are some tweaks they could make to it in the design that would make it more robust, more reliable. And a next version of it would be probably the version that would be the usable version. So we find that often in technology demonstrations. When I first started in this program years ago, I was very pie in the sky about all this. I was like, oh, we're going
One more brief comms blackout, I think.
to demonstrate this one, and that's going to be it. We're going to that way. And we've seen that happen a few times.
Gotcha. That does make sense. It's part of the whole scientific method, right? Like if one little thing doesn't work or you have something else that you need to firm up or didn't quite design or perform the way you wanted it to, you don't just say, oh, well, it failed, just throw it all away. You observe what happened and then you see how you can make changes, you improve it, and you try again. That's literally how science works. It's how engineering works.
That's right. And we walk a fine line because, there's this phrase when you're working, especially with the people who have designed this and put their life's, work into some of these concepts, we like to say better is the enemy of good enough. And so you have to figure out where that line is. What's good enough to go off and, produce? What betterments do you need to make, and your kinds of, and how much does it cost? It's constantly that trade of, but to do this is going to cost so much X amount more that we kind of, don't have. So where can you draw that line and then use it? And it's tough. That's a tough trade to make.
Yep. We still operate in the real world where we don't just ask the magical unicorn for our funding and the unicorn grants us all the space dollars we need or whatever.
Yeah, we're still 100%. Looking for him now. We're still looking for that unicorn.
Here's a question really quickly, and I don't actually know if you can answer this one for us, like if you're allowed to answer it. What is inside the inflatable part of the heat shield? Is it like an inert gas? Is it just air? Like what was inside of that?
Go ahead, Trudy.
Yeah.
Go ahead. You can, if you want.
No,
to
you
can. Nitrogen. It's nitrogen. It's an inert gas. Yes,
okay.
You're right. Nitrogen. Yeah.
Cool.
Yeah.
I was trying to, build the, excitement, and then she said nitrogen.
Nitrogen. No big deal.
I didn't know how to build the excitement to say. I totally failed on that one. I was like,
we didn't need a big reveal. Yeah, it's okay.
Like, hold on. There's a sign behind me. I'm going to turn this. No, there are other concepts though that we're looking at for other gases to use for this. They're not. We have not fully investigated all of them, but there are some other concepts out there for different gases to use, and that's probably as much as I could say about that. So.
Makes sense. Let's see. Again, there's 100 questions in there. I don't want them all to be too terribly complicated, but every now and then I'm just like, I don't know, is it nitrogen? I guess I sort of gave it away when I said inert gas. Anyways.
But speaking of a gas, one of the two technologies that was a part of technology demonstrations on the Mars Perseverance rover. Trudy talked about the terrain relative navigation, which was more of an operational technology that helped, land that awesome rover on Mars. But we also had MOXIE, which is Mars Oxygen In Situ Resource Utilization Experiment, which is why we call it MOXIE, another long name. We just love long names. But that's actually taking that thin atmosphere of Mars, and it's kind of like it's a box which has kind of like an electrolysis plant in it. There you go, that gold box that's pulling in the atmosphere and actually converting it to oxygen, to usable oxygen. And we are now on our 12th oxygen run. I think this week of Thanksgiving will be the 12th oxygen run of MOXIE. And so, certainly this is another scalable technology, and we are working with the folks at both JPL and MIT, the contributors to this awesome technology. And, they have the freedom now, while they're on Mars, to look at several different parameters. What's the best, what's the best way to make this? Are you still making it in a dust storm? How pristine or how pure is the oxygen? They're being able to test it all types of different ways. And it's escaping me right now. I think it's just lack of sleep. I'm sorry, guys, but I'm trying to remember how much total breathable oxygen has been produced so far. And I'm sorry that it escapes me right now, but we are on our 12th run. So we're super, super excited about the success of MOXIE.
That's amazing.
I think it's been so they have produced 98% oxygen purity every single time, which was the level 1 requirement, we like to call it. And I think to date, they've produced about what would be the equivalent of 10 minutes of breathing air for a human being. So you could live for about 10 minutes on the oxygen that MOXIE has produced. So clearly you see the picture there that DOS has up. It went into probably about the size, maybe just of a car battery, maybe a little bit bigger than that, went into the rover. So clearly the scale up of this, just like LOFTID, scaling it up, just scale up of this is something that we have to consider. Right. You'd need significant scale up to be able to produce the amount of oxygen that you need for either breathable air or fuel, rocket fuel, to make that. So, but it's a great first step. It's really the first step into a whole category of technologies we call in situ resource utilization. That's what MOXIE is.
What is the turnaround time for turning it into breathable oxygen? Like, is the goal maybe that, I don't know, somebody could strap on one of these things and it could just constantly cycle out, into breathable oxygen inside a suit or something?
So right now, I think it takes, Tawnya, I know it takes a while for the system come up and get ready to kind of receive the carbon dioxide and then process it. I don't think it's a very quick process right now. I can't tell you exact times, but I would think that would be one of the ultimate goals. But we're talking really large scale production. So I think of it almost as a plant, like a plant type production. I don't think of it as like backpack, EVA type of, it could, maybe if they could scale it down. But I think we've just really been thinking, scale up to this point, because the astronauts have suits, right, where they can do extravehicular activity, but we really need scale up with MOXIE. So yeah, but you ask a good question.
That's an excellent question.
Any others, Das?
I can continue asking questions the entire time here. if you'd like me to. We could probably go for another 2 hours asking all the questions I've got in the queue. Let's see here. I'm trying to make sure we don't revisit. A lot of people are asking the same sorts of things, like, "Oh, could I ride this down?"
That's all people want to know.
Seems
Is
to
it
be
rideable? Can we make a ride out of this?
Quite a bit of
I can see
conversation
that as
about.
being a very popular
So-
for NASA theme park someday. You go
Yeah.
up a big elevator and then hop into a lofted shield and just like whee all the way back down. That'd be amazing.
I was just
would
going to
ride that.
say some theme park needs to capitalize on this. Like I live not far from Cedar Point. If people know where Sandusky, Ohio is, it's like roller coaster capital of the world. They need some kind of high ed ride, I think. Anyway, crazy.
Oh, let's see here. If you have any other questions, folks, tag us in chat. But I'm skipping quite a few here because we've talked about them a lot. Here's one. Okay, this is a good one, and a lot of the viewers are very interested in, not to name names, but larger, shiny spacecraft, right? And so that could be sort of a change. You're used to sort of riding along or having limited space or anything like that. And are there any ideas that you have that you haven't been able to do just because you haven't been able to have the space to do it? And if all of a sudden a big stainless steel spacecraft says you can launch a tennis court, is there anything that you'd be like, wow, that's going to be useful? Or would you just launch a lofted size of a tennis court? Anything like that in the queue that space or volume constraints have made difficult to test so far that you can talk about?
Well, there's lots of things in the queue that would be difficult to launch from the sheer size, like habitats and things like that.
Right.
We've looked at inflatable like habitats. I think that's what the question is. I'm not sure if I understood it completely, but I think there are things we're looking at that would be construction on orbit, larger scale infrastructure needs that we have for our future architectures. Tawnya, you can jump in here anytime too, but I mean, that's kind of the thing I mentioned earlier about in-space manufacturing and assembly. Solar arrays, I mean, manufacturing and assembling those on orbit. Antenna, like someone mentioned comm before, and kind of array antenna, that type of thing. We have a couple of demos now that we're going to look at that. So, and then certainly the larger scale structures that I mentioned, but
right.
I think I understood. Maybe I didn't understand the full question, but
yeah, it's just they were specifically asking about Starship, right? The SpaceX Starship, and the amount of volume that's available there that has been previously sort of not attainable. It's been really difficult to get that much volume into space. And if Starship works out, it may be a lot easier to get a lot larger things. But that's where, like you said, scaling up some of the demonstrations you've done could make sense. Do you need a larger plant to make a lot of oxygen on Mars? Well, you're not going to stick it on the back of a rover. You need bigger cargo area to get that to Mars. So a larger spacecraft like Starship might enable that. Do you need a larger heat shield for this big hab that's going to land on Mars? And it's inflatable, but when you have 8 meters of space to work in, imagine how big the inflatable could be if packed it's 8 meters or 6 meters, right? I think, again, it's the same sort of thing where y'all prove the concept. There's an idea and the math works out and the physics seems like it should work out, but you all get out there and you actually prove, yes, this concept works, and now let's scale it up. Let's put it in production. Y'all are sort of the front line there proving these ideas, right?
Yeah. Yes, absolutely. And I personally, love that model of, because NASA does so much of, the first of, first this, first that, and taking those concepts, taking those proven concepts, and letting industry run with it. I think that's just I think that's an amazing model, and that's Tawnya talking. But I think that's just a great model.
Yep.
That we are the pathfinders. We find the way, we prove those concepts, and then and to the extent that industry is able to take those and run with them.
I mean, that's a great point. You guys really are, at the cutting edge of technology here. You are the ones doing all of this magic. And actually, to your point, Trudy, what you were saying before, how it's so important to see, more of the next generation learning about this, getting involved. Can you both just kind of give us briefly, like, your background, what led you to be able to have these amazing positions and what were you inspired by? I know you mentioned your science club or whatever it was. I had something like that too, actually. That got me very into it when I was in high school. But what was it that really attracted you to this, and what was your path to get to these positions?
Yes. So real quickly, I actually was one of those kids that grew up and I knew I wanted to be an OBGYN. That was what I wanted to do and be. And I summer before my senior year of high school, I was selected to be in this NASA SHARP program, and it changed my life. I saw engineers and scientists who looked like me and who were just rock stars in my world. And then it was really from there I learned about this NASA partnership with an HBCU, Spelman College, which is my alma mater, and I applied for the Women in Science and Engineering scholarship that NASA had with Spelman, and was selected and went to Spelman. And it was a 3-2 program. So it was Spelman and Georgia Tech. So I did chemistry at Spelman, and then the last 2 years did chemical engineering at Georgia Tech. And so that kind of started me on my path to end up here at NASA.
Wow. And Trudy, what about you?
Yeah, so let's see. Growing up, I always loved school, loved school, and did particularly well in math, I would say, math especially, and science as well. And had a dad who worked his whole career as a Ford Motor Company engineer. I grew up in Michigan, and he always encouraged me with my grades in math and science to pursue, an engineering type of degree, and had a lot of teachers in high school. I can remember especially my calculus teacher in high school really encouraging me to look at engineering as well, and happened to live about 30 minutes from Ann Arbor, Michigan, and went to the University of Michigan. If there are any Buckeyes online listening, and please don't hold it against me. I know it's Michigan Ohio State week. It's a big week. I just hope both teams have fun. But anyway, so got an aerospace engineering degree there from U of M, and I think it was really the encouragement of some others who saw some of the aptitudes that I had that really made the difference for me. And my dad would always tell me, he's like, you don't have to stick with engineering as a career, but you can build off of that. You can get an MBA, you can get a law degree, you can become a patent lawyer, and he would kind of run through all the things that were options for me in case, someday I just didn't want to go into engineering. But I will tell you this, that too, with NASA in particular, how you're young and you're kind of like, well, I don't want to do the thing that's most familiar to me. I looked around, and a lot of people I knew that were getting engineering degrees were going into the automotive industry, and I just wanted to see something else. And in high school as well, in my junior year of high school, I was in my physics class, and in January 1986, and Challenger blew up. And this was in the days when they rolled in an audio visual cart with the TV on it. Okay. I mean, kids can't even relate to this anymore. Like, my kids are walking around with their phones, right? And so they would just anyway, they rolled in the AV cart. Mr. Krupka, my physics teacher, stopped class, and he said, we're just going to watch this. And we certainly did. And then coverage of all of that. And it really had an impact on me. And I just always associated NASA with excellence and really big things, bigger than myself. And it was always very compelling to me for whatever reason. And so that's why I chose aerospace engineering. That's how I ultimately ended up at NASA, and have been very fortunate in my career to have a lot of great opportunities. So that's how it happened for me.
That's incredible. Yeah, just the way that so many of these little things kind of add up over your life to bring you to wherever it is that you are. That's so cool. And Tawnya, you were telling us too before as well that you guys now are making more of an effort with this comic, First Woman, right? To try to, and Trudy, you're nodding too, you might be involved as well, to try to really reach more of the youth, through comics and graphic novels. Can you talk a little bit about First Woman?
Yes, that's just such an excellent initiative that NASA started, because our goal truly is to put the first woman or first person of color on on the moon. And so this is just an outstanding. I mean, it's got the QR code that students can access through their phones and go to this amazing story of Callie Rodriguez, who's the first woman. And so we have just been promoting First Woman like you wouldn't believe, and it has just been so well received. And so many enthusiasts and young people have just absolutely loved it. And so I think the first story has been released, and so I think now they're waiting on the second story for that. And so it's just been an outstanding initiative for NASA, and I'm excited about it as well.
And that's available online too, right?
Yes, definitely available online. Absolutely.
Oh, great. We just put a link to it in the chat. So
Great.
everyone please check it out. It's really cool.
Please check it out. It's awesome.
Yeah,
there's an app.
Go ahead.
There's an app you can download.
That's right.
Cool. I posted that link in all of the different relevant chats. So you see that nasa.gov/special/Callie First. If you click on that, you can get over to more information about the First Woman graphic novel.
Very cool.
All right.
Any other questions from the chat?
Well, I had a couple of things actually come in here while we were talking. So let me get just one second. A text message came through on my phone as soon as we mentioned pool noodles. And apparently, folks from the office over there at Lompoc, near Vandenberg Space Force Base, had a Halloween costume for LOFTID, which involved pool noodles, it seems.
You guys are so creative. Oh, my gosh.
This was like a Halloween thing
Yep.
there at the town near the Space Force Base, where LOFTID launched from, right? Launched from Vandy over there.
Absolutely. Those are two of our comm ladies, Kat Botch wearing the actual lofted suit, and that's Holly Ellis in the blue NASA shirt, and I believe the lady in the middle,
the head of the chamber in Lompoc.
Yes, the head of the chamber in Lompoc. So that was just a cool. It was right around Halloween, the first launch attempt. So just had lots of fun with that.
I love it that we talked about pool noodles, and there may or may not have been space pool noodles, and then all of a sudden there's a costume made out of pool noodles.
I'm so glad we had that picture. I was gonna mention that. I was like, we actually made a lofted costume out of pool noodles, and it was perfect.
It is absolutely perfect, and thank you for making my phone buzz there. I got that off the phone so we could show it here.
I love it.
There's a lot of really technical questions that I don't think we're going to go into, but there was one that I really wanted to sort of talk about, and it's sort of how the ideas that the Technology Directorate goes through sort of go from idea to being done as a project, right? And so it's specifically, how does an idea get from a spark to an actual demonstration in space? Is it like one person pushing an idea forward? Is it like an entire organization asking for that? Is it a company coming in for asking it? But if there are great ideas that people have, how can they be involved, and how does that idea turn into more than an idea? Here's Trudy.
Yeah. So I'll start. Multiple different ways for ideas to go along what we call the technology readiness level spectrum, which is from like 1 to 9. 1 is the kind of ideation stage. 9 is it's been used so many times. It's we know it's going to work every single time. And so it depends. It depends where ideas come from. It can be academia. We have this whole program of stuff we called early stage innovation. We give a lot of funding to companies, small business companies, where ideas come from. So academia, individuals with the prizes and challenges that I mentioned, small businesses. We have a whole host of different funding sources where we can investigate some of these things and go from kind of ideation to lab to try to do some early testing, early concept testing. And if it works well there, we'll take it to the next step. So there's a series of next steps. You take it to like a breadboard, which is a low fidelity type of hardware situation, to a brass board, which is a little bit higher fidelity, to some more higher fidelity hardware that we produce, and then we test in a lab on the ground. And that's kind of the technology maturation piece of it, where it's coming up through that kind of pipeline, we call it, and going through that testing.
Is that the technology readiness level? Is that the pipeline you're sort of talking about there?
It's a scale. That's really the scale by which we measure, where it's like looking at it like this and saying, we think it's approximately 4, which is like a brass board, or you're
Did I
showing
find
it there.
Okay, I was asking if I found the right image there before
there's
I
a
showed.
number. I mean, you can look it up. You can Google it online, and there's a number of them. But I can't see it from here. It's tiny, but it looks about right.
Yep.
9 would have been like shuttle, anything we used on the shuttle over and over and over again. Okay, that was a TRL 9.
Yep.
As an example. So we bring it up through that pipeline, and I don't know, there's just various sources that we have to find the ideas to begin with. And then when it gets to a point where it's done well in all the ground testing, then we can take it into the relevant environment testing we've been talking about for the last bit of time here. And it gets more mature every single time we do the subsequent testing to it. So that's kind of the process. There's pitfalls along the way. I'm not going to make it, all rosy. There's definitely pitfalls along the way. Sometimes technologies need advocates. I mean, it's not just how's it doing in testing. Sometimes you need that person who will champion that technology and go to headquarters and say, this is why you need to care about this. I've seen this conversation happen over and over and over and over again. This is why you need to care about this. This is why you need to invest in it, because you don't always have, that full awareness of, there's so many competing priorities. I'll say that there are so many competing priorities for the very little bit of funding that, and I shouldn't say it that way, but comparatively speaking, as one of the agencies that's on the discretionary side of federal budget spending, NASA doesn't get a whole lot of those dollars, comparatively speaking. So we have to really be wise with how we spend the amount of money that we're appropriated. And we do take that very seriously. We really do, and how we spend that money. We are not, our goal is to not invest in things that don't have multiple uses, are not cross-cutting, things like that. We have those conversations internally all the time about those best investments. So, it's hard. It's hard. We could fund X number of times more than we actually do, right, Tawnya? I don't even know how to put a number on X, 10, 20, 30, 50, times more. We could fund so much more than we actually do, just because of the limitations on our appropriations. So that we're grateful for, but we have to be wise about how we spend it.
Yeah,
absolutely. Which is why we want to take what Trudy and I often refer to as NASA takes smart risks. That the risks have to be smart in this whole process.
Makes sense. There's a lot of great ideas and only a certain amount of resources. I think we all wish there were more resources sort of diverted in that direction, but you do have a process that you go through to sort of decide, hey, let's focus on this, and then this, you're going to table this for later, that sort of thing. Unfortunately, you do have to sort of select out what you spend your time, energy, and resources. I mean, money on, really, right?
Sure. Ross, I should also mention real quickly, if I could. I'm sorry.
Sure, of course.
In space tech, there really is like a sort of a spectrum of programs where, the technologies that are selected for certain programs kind of run along that TRL pipeline, that technology readiness level pipeline. And generally, we say there are exceptions. There are always outliers, but generally, the missions and projects that are within TDM, Trudy's program, my program, are generally in the 5 to 7 range of that TRL level.
Gotcha.
But we've got some great examples of that progression. And we're trying to do better, really. And Trudy can talk about this as well. We're trying to do better at progressing technologies through that pipeline so that it's a very smooth transition, and that we've got the right type of, estimate for what this technology is going to cost in terms of its life cycle costs over its life.
Yep.
And just making that smooth transition. One of the amazing examples is the ROSA, the rollout solar arrays, which began in that SBIR, one of those early stage space tech programs, and the success of it and what it's been used in. So that's just a great example.
Gotcha. So it's not just, you don't have like a wacky mad scientist with hair coming in talking about flux capacitors. It's not just a random idea. The ideas sort of reach a certain level of maturity, and then when they come across your desk with your group, it's time to test them. Like, let's actually demonstrate this technology. It's right there in the name, right? Technology demonstration missions. We're not just whiteboarding things or brainstorming raw ideas. It is something where it is time to get the truth on whether this works the way that we think it's going to work. And that's where y'all come in, right?
Exactly.
Yeah, but not only that, I'll say too, we match it up with NASA has a whole host of things we use as kind of guide stars on how to make these investments and by when they're needed. So it's kind of a big puzzle. It's a big dance of, we want to be here by 2035. Well, to do that, you back it up from there. Okay, what do you need by when? By a project's preliminary design review, by its critical design review. When do you need certain things? And so we have roadmaps, and we have envisioned future priorities, and then we have these blueprint objectives. So we have several different sources of information for when do we need things by then, and that helps us guide things too on, okay, if we invest in it now, it'll be ready by the time we need it. Oh, well, we need this one earlier. We better, move this to the left, or we need this one later. We can wait a little while to invest in those things. Right. So that's a big piece of it too, is the timing of it all. Cost equals schedule. Kind of money is time, and that's true for us too. So it's a big puzzle on how we put that all together.
Excellent point.
Yeah. Gotcha. Again, I can keep going through questions all day. Were either of you involved with the green propellant infusion mission? Was that one of the things under? Okay, y'all are nodding.
We both were.
Somebody in chat is very interested in the green propellant infusion mission and keeps asking questions, and I'm like, I don't know if we're talking about that today. They were asking about the status and were you involved and is it successful and any ideas for using it? Like, talk about green propellant infusion mission there for this one person in chat.
I think we both can. I'll just preface it by saying that when I came into TDM, GPIM was an established mission. I think it was developed over about 10 years, if I'm not mistaken. But it actually was a major launch for TDM, one of the technologies that we launched. It actually launched along with DSAC-2, Deep Space Atomic Clock. I'm sorry, did I say DSAC-2? I meant DSAC, okay. Deep Space Atomic Clock. Those were two missions that launched on the U.S. Air Force SPT-2 mission out of Cape Canaveral, and I believe it launched about June of 2019 is when it launched. And so yeah, GPIM was our partnership with Ball Aerospace, and it had about, I want to say, about a 13-month run. But Trudy, I think you were the program executive for TDM when it came into the program, correct?
I was also the person. Before that, I was at Glenn Research Center and got the call from Ball Aerospace that they wanted to partner with us on this. Glenn Research Center is known for being a power and propulsion expertise, the idea there was to use an Air Force developed monopropellant, not hydrazine. Hydrazine is highly toxic for ground workers, and the Air Force developed, it was called AFM 315E, but now it's called Ascent, because I think AFM 315E was not something people easily remember.
Hard to say.
It always just stuck in my head because I'd seen it so many times. On charts and things, right? And so that's the monopropellant, non-toxic monopropellant that they designed this around. And the thruster itself was supposed to be a 10 Newton thruster. There were problems with that thruster. They scaled it back to a 1 Newton thruster. That was a Ball partnership with Aerojet Rocketdyne. So Aerojet supplied the thruster, Ball supplied the BCP-100 spacecraft. And so that is what we went with. The demonstration itself was highly successful. But I would say the usage of that technology to date has been maybe a little bit disappointing. Thought that it would really be infused into some product lines and things like that, and still waiting on that to happen.
Right.
So successful demonstration, but usage of it, not as much. I think the fuel itself is doing quite well. But I think, that the product line that uses that fuel still has to materialize. So
gotcha.
Yeah.
So people are still filling their spacecraft with spicy orange gas, I think is how we usually refer to it. Do not.
And if you were to actually look at the green propellant, this was one of the cool things. It was actually like more salmon in color. It wasn't actually green.
It wasn't actually green.
Salmon.
Actually green, more salmon in color. But but Trudy's right. It's been a little bit it hasn't taken off like we would have expected, it to be what we thought, as a really cross-cutting type of technology. But one of the great things about it, in terms of access to space, people could actually fill spacecraft in their shirt sleeves. I mean, that's
right.
Unheard of, versus using hydrazine. And so has some really great. And so we're certainly not giving up on that, but we think it has some potential.
I bring up a picture of people working on a spacecraft that filled with hydrazine, but I don't want anybody to come after me for showing the wrong spacecraft. If you've ever seen, like, when certain little spacecraft that like to stay in space for a long time and nobody knows about them, come back down and land on the runway, and you see the people in the full body protective gear, right? That is a spacecraft that uses some of the non-green, let's say, propellants, hydrazine like you were talking about there. And it requires a lot of personal protective gear. You do not want to breathe the gas that stuff is. So the green propellant is a totally different thing, but not quite being adopted yet, it sounds like, right? Okay, we have been going for more than an hour and a half. I think we might have kept y'all a little bit over here because we just started talking about random missions, then another one came up. But I do believe we are coming to the end of our show here today. Trudy and Tawnya, thank you so much for spending time on the weekend here and just having a fantastic conversation about your experiences working with all these technology demonstrations.
Yeah, the stuff you guys do is so incredibly cool. And I'm sure everyone out there watching is just blown away and can't wait to hear more and see more about all of these cool things that you're doing.
Thank you for having us. I know Trudy can speak for herself, as you've heard, but we are so excited. We were so excited to be part of this conversation today. Thank you for making it so fun.
Well,
yeah, thank you. Thank you for having us. And I'm really impressed with your audience. I'm impressed with both of you. I don't know if you're off there studying or reading space news or whatever on your free time, but I don't even know how people in your audience know about Green Propellant Fusion Mission, this thing we did a couple years. That's impressive.
One person did. One person asked like 4 times about the GPIM.
Outstanding.
That people can cite technology demonstration missions as even part of our program and know what that is. That's darn impressive to me. So
you're
thank
making
you
a
for
difference.
You
are
are.
definitely making an impact out there.
I would just say thank you for the interest in this. It's not the premier stuff that NASA does with big Artemis missions. I really mean that. Like, we often feel like we are behind the scenes doing things you will hear about in 10, 15, 20, 30,
Right.
40 years that we're enabling. By that time, I'll be long gone. Oh, the dog just busted in. My dog. Anyway, my dog's
That's okay. It's okay. The dog is coming to end the show. Like,
exactly right.
dog might have got a computer cable
here.
too.
And so thank you.
Too funny.
I think we might have had a pet-related incident. There we go. Okay, Trudy's back. All right.
There she.
The dog's going to get into the show in the background as well. Trudy, it's absolutely fine. Not a big deal at all. Again, Trudy Trudy and Tawnya, thank you so much. Y'all are part of NASA's technology demonstration missions and the Space Technology Mission Directorate. I really do appreciate y'all spending time hanging out with us. I'm glad you had some fun. I know sometimes we tell some jokes when we talk about pool noodles and stuff, but also a lot of very technically minded folks watching. And it's always a blast having interesting people who do awesome things in space on to chat with us. We really appreciate y'all taking time out of the weekend.
Pleasure to be here.
Next
Thanks
up,
again.
y'all, coming up is going to be next month's Virtual Astronomy Live. I got my housekeeping stuff here, and I have to click through. There we go. Okay. We're actually changing the name of the show next month. It's going to be Intrepid Museum's Astro Live.
That's right. We realized, we talk about astronomy sometimes, but we talk about a lot of other cool stuff like LOFTID and Psyche and, all of the other cool things that we do quite a bit more. So we are actually going to be changing the name ever so slightly. Intrepid Museum's Astro Live is how you will now be seeing it in the future, starting next month. Same great show, just a little tweak of the name. And yes, our next show will be Sunday, December 18th, 3 o'clock. And the topic, we are still confirming our final guest details, but I will give you a teaser. It will probably be about a historic mission to the moon. It's vague enough, but very specific at the same time.
So start
take that
thinking about
information as you will.
it's historic missions to the moon, and what could that mean? Our options have recently expanded in what that may mean. Also, folks, remember that the Virtual Astronomy Lives don't just magically happen. They're supported through the NASA Cooperative Agreement awarded to the New York Space Grants Consortium. Massive thanks for helping us make these happen. As also, we keep doing these shows because y'all keep showing up. The viewers who are watching at home, asking fantastic questions, all the different channels on Facebook and YouTube and all the different places that you can experience this. So once again, Trudy and Tawnya, we really do appreciate y'all. We had a great time, but for now, that's going to be the end of this month's Virtual Astronomy Live, and we will see you nerds later. Thanks again for watching, everybody. Bye.
Thanks, guys.
Propulsion continues to be normal.
RCP chamber pressure looks good. Toggling up.
Roger, roll, Atlantic.
Water towers, fly!
Tango Delta nominal.
Body mountain SC off. Bring in SC off.
Yikes. You bet. Concur. We don't need any more of these.